In this video, we'll give an overview of our work on learning to compose domain-specific transformations for data augmentation, which we'll be presenting this year at NIPS. All of our code can be found on GitHub, and other related material can be found at snorkel.stanford.edu.
Data augmentation is the technique of artificially expanding labeled training sets by transforming data points in ways that preserve class labels, like small image rotations or random crops. Data augmentation has become a critical tool in deep learning pipelines, and it's used in nearly every single state-of-the-art image classification result today. It can also be viewed as an important form of weak supervision, allowing domain experts to inject knowledge of task or domain-specific invariances in a simple, model-agnostic way.
That said, data augmentation pipelines can be tricky to set up, with a large variance in end model performance based on the specific approach used. This stems from the fact that while it's often easy to come up with individual transformations that preserve class invariance, figuring out how to best tune and compose them is a labor-intensive and time-consuming task.
Looking to the success of data augmentation on well-studied image tasks with simple transformations, we'd like to make data augmentation easier to use in other domains such as natural language processing, and with more complex augmentation strategies such as ones drawing from medical expertise. With these goals in mind, we have even more of a need for automated ways to help develop good augmentation pipelines.
In our approach for automating the development of data augmentation pipelines, users provide a set of black box transformation functions and unlabeled data. We then learn a model to tune and compose the transformation functions automatically. This model can then be used to perform data augmentation for any end model, such as a CNN for image classification.
To accomplish this goal, we adopt a view of augmentations as sequences of incremental transformation operations provided by the users. This gives a simple and tractable way of tuning and composing the transformation functions.
To learn this sequence model, we make the key assumption that transformation functions will either preserve the class label or map the data points into a garbage class. To illustrate this assumption, we tried to randomly augment the images in the left column to make them look like the other classes to a pre-trained discriminator. Clearly, we weren't very successful. For example, none of the images in the cat column look like any cat that has ever existed. Crucially, this weak class invariance assumption allows us to use only unlabeled data to train our augmentation model.
To train our model, we use a generative adversarial approach. In this setup, the generator is a sequence model over transformation functions, and the discriminator is trained to discriminate between augmented and unaugmented data points. This forces the generator to produce transformation sequences which yield realistic-looking data points, and we also add an objective term to encourage diverse augmentations. We train the entire model using policy gradients to allow transformation functions to be non-differentiable or stochastic.
In our experiments, we explored two generator types, an independent model, which only learns the sampling frequencies for the transformation functions, and an LSTM generator, which can learn to compose transformation functions in specific orders.
Using our approach, we see strong gains over standard heuristic augmentation approaches for image classification tasks, relation extraction tasks over text, and a mammography imaging task in collaboration with radiologists.
For more, stop by our poster on Wednesday and try out our easy-to-use code up on GitHub.
See you at NIPS!